So far we have addressed, in the previous part, we have addressed the case of zero input and analyzing the output from the system only due to initial conditions. Now the more important part for us is, as people who study signals and systems, is the other part. If we set the initial conditions to 0 and drive the input of the system with some signal, how can I evaluate or calculate what's going to be the output from that system? Okay? Before going into that part, we need to look at some important finding from mathematics, and it has nothing to do with system up to this level. Okay? Remember, and you have been probably doing this in some of your math courses or some other engineering courses, any signal, any function of time, x of t, right, which is typically a smooth signal, it's continuous, so rest to time, you can always approximate that by a step or a staircase function, like this one, right? And you probably have done that in some of your courses to make the analysis easier on you, okay? So I can say that this smooth curve is approximately represented by pulses, because each one of those is a pulse of constant value, and it exists between this start point in time and finishes at this end point in time, right? And if I add those pulses, because they are one next to the other, if I add them, they don't overlap. So you end up with this staircase representation, which is trying to track the actual signal, but it's slightly different. And that's why we say that this is an approximation. X of t is approximately equal to those pulses. P of t is a pulse with amplitude equal to 1 and a width equal to delta t, right? Okay. Now, in order to make the amplitude grow with the curve, we multiply it by the value of the curve at the start of this pulse. So whatever the value here is multiplied by the amplitude of a unit pulse to make it a higher pulse that reaches the curve, right? So we can say that this curve can be approximated by summation of those pulses. So P of t exists at 0. P of t minus delta t is the first pulse here. P of t minus 2 delta t is the second pulse, exists in this location. T minus 3 delta t exists at the third location, and so on. So these are pulses one next to the other, and the amplitudes of each one is growing according to the value of the curve at the start of the pulse. Okay, so we have different amplitudes for those pulses. If you add them together, you get the staircase representation that you see there. It's not exactly equal to the signal, so we say that this is an approximation to x of t. How do we make that approximation become closer and closer to exactness? If you take the limit as delta t becomes very small, so those are going to be much narrower and they become one adjacent to the other. Okay? And then accordingly, they are actually going to trace the smooth curve without any staircase action, right? If they become narrower and narrower, and they adjust directly to the actual curve. Now, when you do that mathematically, you end up with moving from this representation. When we add things together, when we do a summation over discrete values, and then we make those discrete values grow in terms of their number, and they become close to each other, such that each one of them is almost with 0 step from one to the next, then this summation becomes an integration. That's the definition of an integral. Okay? And this n delta t, rather than being a discrete variable that has a value, for example, if delta t is 1 microsecond, then it has a value 1 microsecond, 2 microsecond, 3 microsecond, 4, and so on. If you take delta t smaller and smaller, it becomes, n delta t becomes a continuous variable in time. We call that tau. Okay? Now, in order to represent this as an integration, we always need in the integration the d tau, right? That's a delta t as delta t goes to 0, right? So this d tau is simply This is delta t as it goes to 0, becomes d tau, okay? So in order for that to appear, I need to do the following. Just multiply this by delta t and then divide over that again here. Right? Okay? Did I do it? Did I change anything here?
No.
No. I multiplied by something divided by it. But I need to keep this, so it will become the d tau. And notice here what happens to this pulse. The amplitude of the pulse grows as you make it smaller, right? Such that the total area under the pulse stays the same. Right? Okay? And this is the definition of what? A delta function. Remember, when we defined a delta function, we said that you can think of it as a pulse, but you make that pulse narrower and taller up while maintaining the area under the pulse exactly the same, right? So that's exactly what's happening here. So this, as we take the limit as delta t goes to 0, becomes a delta function. And it is shifted at location tau, which is the n delta t that we see here, right? And it is scaled by a certain factor, and that factor is x tau. So we end up with a general expression without any approximation now, because as we take the limit as delta t goes to 0, it's no longer an approximation, it's an actual representation. A general expression that says that any function, any continuous time function, can be represented as an integration of delta functions shifted in time, right? Okay. Using this representation. We just started by this approximation, and as we made it no longer approximate, we ended up that any x of t can be represented as the values at different time locations tau multiplied by shifted deltas, or basically the x of t is the summation of deltas, but since the deltas are very narrow, it becomes an integration. So we represent a function by summation of deltas, or integration of deltas. Okay? Type. Why this is useful? We will see.
Gives the actual.
Listen, hi Ben. Wait. Imagine that I'm dealing with, forget about this now. So just keep this on the side. Imagine that I'm dealing with, in all this, we are dealing with linear time invariant systems. Right? So for a linear time invariant system, if I scale the input by any value, what happens to the output? Gets scaled with the exact same value. Right? And if I shift the input by any time shift value, what happens to the output? It stays the same, only shifted with the exact same shift value. Right? That's the main property of a linear time invariant system. Right? So for a linear time invariant system, if I know that x1 of t produces y1 of t, right? Then ax1 of t will produce a y1 of t, right? That's by definition, correct? And also x1 of t minus some shift, well, let's not use tau so it doesn't get you confused, let's call it t naught, okay? Is gonna produce at the output the same output that comes for x1 but shifted. So y1 t minus t naught, right? Not only that, if I know also that x2 of t produces some output, call it y2 of t, then if I put into this system x1 plus x2, what do I get at the output? y1 plus y2. All of these are properties of linear time invariant system. Okay, why these properties are useful? Okay, because now I can, knowing that any signal can be represented by some summation, this is eventually a summation, even though it's an integral, just summation. Some summation of scaled and shifted deltas, then it's probably, for a linear time invariant system, it's sufficient to know the output for a delta input, and then based on that, I can calculate the output for any general input. What do I mean by that? Let's go back to this LTI and think again. If somehow I can go to the lab and put into my system a unit impulse and then measure the output from that system. So my input x of t is actually set to be a delta. I will bring my system, put it in the lab, and somehow from a generator, I will generate just a quick impulse, right, with very high amplitude, very short time duration, almost zero, so very quick. And I'll put that, and then the output of that system, I'll connect it to a spectrum analyzer or whatever, and measure, or maybe oscilloscope, and then see what's gonna be the output. Again, don't forget that the input is gonna just impulse and disappear, right? That's a natural impulse, okay? It will not stay forever. However, the output might be something like a decaying exponential, for example, right? So it will just quickly produce an exponential and then it will decay with time, even though the input disappeared, right? We call that the output that I measured from that system for an impulse input. We call that the impulse response h of t. So this is called impulse response of the system. What is the impulse response? Is whatever output that comes from the system when you force the input to be a delta function. That's it, okay? Again, assuming that the initial condition was zero. So we did not have anything charged or anything put inside the system before putting the input. It was initially at zero initial conditions, okay? If I can do this, if I can measure this or calculate it somehow, the h of t, the impulse response, the response of this linear time invariant system for an impulse input. If I'm given a generalized input, so instead of an impulse, now someone tells me what's gonna be the output from this system without measuring it in the lab. Can you calculate the output from this system if I put a cosine into the input? I will tell him or her, yes, I can. Why? Because generally speaking, I can describe this cosine in this form, right? So if x of t, for example, was a cosine function, let's say, okay, then I can write this as an integral from minus infinity to infinity, cosine omega tau, right? Multiplied by delta of t minus tau d tau, right? Correct? Okay. And each one of those terms that are inside here is simply what? As a function of time. This is simply what, and this is simply what? As a function of time t. This is simply a shifted delta, and it's multiplied by some constant, because this is not a function of t. It's a function of the integration variable tau, right? So I know that this, each term of those is just a delta shifted with some value and scaled with some value. If I know that for a delta without shift and scaling, I get h of t. If I go to this and shift it by tau, what do I get here? H of t minus tau, right? And if I scale it by this factor, what do I get here? The h multiplied by the factor, right? So for this being put into the input, which is part of this system, why it's part? Because I don't only put this one, but I put many of them added together, that's the integration, right? So for a single one of those, I know exactly what's the output gonna be, given that I know what's h of t, right? So for each one of those, at the output side, for this, I will get at the output cosine omega tau h of t minus tau, right? That's for a single term of those, without doing the integration, which is an addition of many of those terms for different values of tau, right? Okay? Now, if I do the addition at the input, what happens at the output because the system is linear? Those different terms are added together, which means I still have the integration, right? So I still have, that's the addition, right? D tau. But then this now becomes the expression of the output, right? This is a single term of those is the output that I got for a single term of those. When I add those terms all together, I get the input. When I got all those output terms and I add them together, I get the total output, right? So now I figured out an equation that allows me to calculate the output of the system knowing two things. Number one, of course, I have to be given the input. So I have to know what's the input, right? Number two, I have to know about my system, what's the impulse response of the system. So it's sufficient for a linear time invariant system to know the response of that system for a unit impulse, and we call that the impulse response, h of t. And once I know that, if I'm given any input, I can calculate the corresponding output using this equation. This is called the convolution equation. Okay? Any questions up to this level? To a unit impulse. Yeah. If that response to a unit impulse is called h of t. I'll just make this smaller so you can see the whole picture. Okay? So if that response of the system to a unit impulse is called h of t, and I know it somehow, I know that impulse response, the output from the system given a delta at 0 with only unit amplitude, right? That's an information that I was able either to measure it in the lab or calculate it somehow. It's a characteristic of this system. And my system is linear time invariant, don't forget that. Then again, because I can represent any function as an integration of scaled and shifted deltas, then the output becomes an integration of scaled and shifted impulse responses. Right? Okay. خلاص? And we call this expression اللي هو طبعا هنا انا كاتبه as an example, but the general expression is y of t is equal to the integral from minus infinity to infinity. Whatever your input is, multiplied by delta of t minus tau, t tau. Okay, we call this the convolution integration. It's a way to calculate the output of a linear time invariant system for any given input by knowing only the impulse response of the system, which, sorry, h of t, not delta. H. Okay, by knowing only the impulse response, h of t. Okay, this is called the convolution integral. I will stop at this point and we'll take. So again, in this slide, it just summarizes what I have been trying to do in terms of showing you where we got that final expression, how you can calculate the output of any linear time invariant system from the input to the system and the impulse response. My question to you again, okay? Do you understand what is the meaning of an impulse response of a system? Is it clear to everyone? That's the critical point. Do you understand what do I mean by the impulse response of a system? It's the output from that system when I drive it, when I put at the input of the system a delta function. Okay? So if I give you this, just to see if you understand what I mean. If I tell you that a system is given by the input-output relation y of t is equal to x of t minus 3, and I ask you to calculate h of t of this system. Calculate the impulse response. What's the impulse response for this system?
H of t minus 3. But there is no delta.
Anyone? What do you do? We said that h of t is the output when the input is set to a delta function. Where is the input in that equation? X, right? So you have x of t minus 3, and in order to calculate the corresponding output, you apply to this equation. So what do you need to do? Go and replace the input by a delta function, right? It will become what? Delta of t minus 3, right? Because x of t is replaced by delta of t, then the output is gonna be the x of t minus 3, which is a delta of t minus 3. You got the idea? You replace to get h of t. You set input, which is x of t, to become delta of t. تمام? If I put x of t to become delta of t, what's going to be the corresponding output from this system? Yeah. So replacing x of t by delta of t in this equation means that I have to have here delta of t minus 3, because here I'm not getting x of t, I'm getting x of t minus 3. So the x of t itself is replaced by delta, then the x of t minus 3 becomes delta of t minus 3, right? And that is going to give me the output, and that output for a delta input is what I call h of t, right? So the impulse response for this system, the output from this system when the input is a delta function is simply a shifted delta. And by the way, we call this system a delay system, right? We put a delta to it produces the delta shifted a little bit. Yes? Sorry? Delta of t minus 3. That's the output for an impulse input. Think of it this way, right? Just to remove any further confusion, right? This is the system that I'm talking about. The output here of this system and the input to this system is x of t, okay? For whatever input x of t, the output is gonna be the x of t minus 3. Whatever input I put into this system, just give me a minute. Whatever input I put into this system, the output coming of that system is gonna be the input shifted by 3, okay? So now if I want to calculate h, the response of this system to a delta input, what do I put to the input? Delta of t. What will I get at the output? Right, and that's what I call h of t. Yes?
I wanted to ask, is it always shifted? If it's delay, is it always shifted? Or how do we know that it's a delay system?
It's a delay system because, again, what does it do? It takes the input and shifts it by 3, right? So that's causing a delay. Shifts it to the right. If it shifts it to the left, that's not a delay. That's an advance, which is a non-causal system, right? Okay? So is it clear when I talk about the impulse response of a system, what does it mean? And I was talking to you about, rather than having some equation, you go to the lab because you don't have that equation, you don't know it. You go to the lab, you put a delta to the system, and you measure whatever you get at the output. It might be anything. It might be a shifted delta like this case. It might be for another system some exponential. It might be a cosine. You don't know, right? It depends on what the system internally is doing. What we care about is the output for a single pulse delta with no shift and with one amplitude. The output that I get from the system for this input is what I call the impulse response, h of t. Okay? خلاص؟ طيب. Okay. The right figure is trying to tell you, and I'm not going to elaborate on that a lot. The right figure, figure B here, is trying to tell you that the same approximation that we did using pulses, and we ended up representing our signal as an integration of deltas, shifted and scaled. You can do it also using unit step functions, and you can represent your signal generally using a summation of shifted and scaled unit steps. Okay? That's called, and accordingly you can have something called the unit step response for a system, the output for an input unit step, and you can use that also to calculate the output for any given input. But in this course, as far as I'm concerned, we'll focus only on the impulse response representation of the system and the representation of any function as an integration of shifted and delayed deltas that we talked about, okay? The other possibility is there, just in case you see it in this textbook or other textbooks. It's there, but we are not gonna be concerned with that. Most importantly is the impulse response representation h of t for the system and the convolution integral that we have here that allows you to calculate the output for any given input and knowing the impulse response. That's what we care about, okay? Don't forget that this whole story that we are talking about here is only applicable for linear and time invariant systems, right? Because without those two properties, even if I know the response for a delta, I don't know what's the response for a shifted if it's not time invariant. and I don't know what's the response of a summation of deltas or a scale delta if it's not linear, right? So only because of linearity and time invariance, knowing the response for a single non-shifted and non-scaled delta allows you to calculate all the other responses for any shifted and any time scale delta using the linearity and time invariance property. Otherwise, this whole derivation would not have worked in the first place, okay? Okay, so now it's down to an important part. In order for me, when I'm dealing with linear time invariant system, to be able to calculate the output for any given input, I need, first of all, to know the input. That's going to be given to me. Someone going to ask me, calculate the output for example, a unit step. Calculate the output of this system for an exponential, rising or falling. Calculate the output for a cosine. So someone, definitely to calculate the output for a given input, the input must be given, right? Now it's down to how can I figure out the impulse response, okay? Again, I told you can do it in the lab. Practically speaking, not true. Can you actually generate an actual accurate delta in the lab? You cannot, because you need a signal with infinite amplitude, right? And very short time duration. That's impossible to generate using any electronics or any practical system, okay? So saying that we can measure it in the lab, yeah, you can do it with some approximations, but it's not gonna be really an impulse response. So what's the other option? If I know the differential equation that represents the input-output relation of the system, I can actually calculate the impulse response of that system. So for a linear time invariant system, if I know the input-output, back to this equation, right? Input-output relation using the generalized differential equation representation, okay? If I know that, I can calculate H of that system, calculate it mathematically. How do you do that? Again, there is like a full appendix in the book that describes the mathematical proof of what I mentioned here. You are not required to go through that unless you want to enlighten yourself more in the mathematical aspects. But what we really care about is this general formula allows you to figure out the impulse response h of t of a system, okay, by knowing only its input-output differential equation representation. Okay? It says that if I know this representation, of course this means that I know the Q and I know the P of D, right? Okay? If I know this, I can immediately calculate the impulse response of this system by applying this equation. Let's look at this equation to figure out what do the different terms there represent, and then if we get a little bit more, few minutes, we can do one example. If not, we can do the example next time. The equation includes a unit step function, that's we know. We know what's a unit step function, right? U of t is a function that is equal to 1 for positive side of time and is equal to 0 everywhere else, right? P of d is the polynomial derivative of the output side of the differential equation representation, right? So it's this part, the part that affects the input. And to remind yourself always that in this case, when you are trying to calculate the impulse response, as opposed to the case when we were trying to solve the characteristic or the internal or the initial condition, in the case of the initial condition, we set this to 0 and we only depended on Q of D. But now we are looking at the output for a given input, so definitely we need this, not the other one. Still, we still need this, but for something else, okay? So the part here uses the derivatives, the derivative polynomial of the input, because no longer this is equal to 0, right? This is actually equal to a delta function. That's the input that we put to get the impulse response, okay? Now, what remains is what's y of n? Y of n is the characteristic solution that we did at the start of today's lecture. The solution for 0 input and only initial conditions, right? So again, how do I get that? Of course, as we did before. You solve this polynomial, replacing d with lambda. You get the values of the lambda. Once you get the values of the lambda, you end up with summation of exponentials with constant terms. And then you need to figure out the constant terms. Now, to solve for the constant terms, you need to apply the initial conditions. Let's not forget that in this case, we are solving for 0 initial conditions while we set the input to some value not equal to 0, right? Because we are trying to get the output for an input and 0 initial conditions. So always our initial conditions are going to be zeros, except of one thing. Why that one thing is different has to do with the mathematical derivation. You can go and check it. The last derivative, the highest derivative of the initial conditions, which is just one less than the order of the Q polynomial, right? That one is equal to 1. So all the other initial conditions, while 0, the first derivative with respect to time of 0, the second derivative, third derivative, up to n minus 2, all of these are equal to 0. Why? Because we are dealing with 0 initial conditions, except for the last one, the highest one, that is equal to 1. Why we have that condition? Because again, the impulse input is a very special case. It occurs actually at time 0, right? So this means that even though my initial conditions at 0 were all 0, but now at 0 I put an input, so that plays a little bit with the initial conditions. Mathematically, the effects ends up that I have to set this particular derivative to be equal to 1. Okay? So these are the initial conditions. Why do I need them? Because in order to get y of n, after solving for the lambdas, I need to figure out the constants. I figure out the constants by applying the initial conditions, right? So if I've done this, I've solved this whole part. What remains is this, right? This b of 0 is actually, imagine that, for example, I will just simplify it by giving an example for it and we'll stop there, okay? Imagine that this was something like this, okay? So d squared plus 3d plus 1 of y of t is equal to 2d squared plus 1 x of t. Okay? What is b of 0? b of 0 is this coefficient. The coefficient of the highest derivative of x if n and m are equal. So if the derivative of x reaches the same order of the derivative of y, then this coefficient of the highest derivative of x is what we call b of 0. Okay? Now what if it's not the case? What if this was something like this? d plus 1, for example, x of t. So we don't have a second order. Then this, in this case, b of 0 is equal to 0. And this whole term disappears, right? So this term only exists when m is equal to n. The order of the derivative on the right side, which is the derivative of the input, is equal to the order of the derivatives of the output. If that's the case, then this is not equal to 0. And what does it equal? It equals the coefficient of the highest derivative of the input. In the case that n is greater than m, b of 0 is equal to 0. Okay? Because there is no second order or there is no higher order derivative on the right side that reaches the same order of the left side. Okay? By this we see how we can get all this expression. If we can get all this expression, we got the impulse response. So knowing the differential equation, input-output relation, we can calculate the impulse response. Next time, inshallah, we will do an example on that will clarify that the process is not as complicated as it looks. Okay? Much easier when you do the actual calculation. See you next time. Like an example on this so that we can understand how things are happening. So this is a system which is given by this linear differential equation. So again, from what we have been describing, this should be your Q. This is your Q of D, right? And this is your P of D. Okay? That's the polynomial of derivatives of the input, and the other one is the polynomial of derivatives of the output. Q of D is the polynomial of derivatives of the output. Okay? And the general solution, remember, the general solution says that the impulse response, h of t, is equal to b naught delta of t plus P of D, yeah. multiplied by yn of t, right? And then this whole thing is unit step of t, okay? This is the general expression of the solution. So now we need to figure, we know what's p of d already, it's d plus 1. So that's something that we know. The question is, how do we get yn? Again, yn in the general formula is equal to c1 e to the lambda 1 t plus c2 e to the lambda 2 t. Why do I stop at only two terms? Because the order of the derivative up there is 2, right? Which means that we have only two terms, right? N is equal to 2. So we have only two terms, okay? So how do we get those lambdas? We plug the lambda into this, so q of lambda. So replacing d with lambda is equal to lambda square plus 5 lambda plus 6, right? And this has to be equal to 0. So I need to solve this equation to find the values of lambda, right? How do you solve this equation? Lambda square plus 5 lambda plus 6 equals 0. Just, yes, lambda plus 3 times lambda plus 2 equals 0, right? So this has two solutions. Lambda 1 is equal to minus 3. Lambda 2 is equal to minus 2. Tamam? We plug this back in. So we have yn of t equals c1 e. Lambda 1 is minus 3, so minus 3t plus c2 e to the minus 2t, right? Those two solutions, okay? Now we apply the initial conditions. What will be the initial conditions in this case? Yn of 0 is equal to 0. Y dot n of 0 is equal to 1 or 0? Why? Because again, the n here is equal to 2, right? So we said up to the order n minus 1 derivative, right? So order n minus 1 derivative is the first derivative. So that derivative is going to be equal to 1, right? The initial condition for that one, right? So we know those two initial conditions. Let's plug them in. So y of 0 is equal to 0, which means that this is equal to 0 when t is equal to 0. So c1 plus c2. Plus, because if you put t equals 0 here, you get what? 1, 1, right? If you put t equals 0 here, you get 1. If you put t equals 0 here, you get 1. So this becomes only c1 plus c2. And for that, for the case of t equals 0, the y is equal to 0. So this term is 0, right? This is applying the first initial condition. The second initial condition, you need to take the derivative first. So y dot n of t is equal to minus 3 c1 e to the minus 3t. I'll use a... Okay. Y dot n of t is equal to minus 3 c1, the derivative, right? E to the minus 3t minus 2 c2 e to the minus 2t, right? Just take the derivative of this equation to get the y dot, derivative with respect to time, okay? Now, for that, apply the initial condition. The initial condition says that at t equals 0, when I put t equals 0, I get here minus 3 c1 minus 3 c2, right? At t equals 0, the y dot is equal to 1. So on this left side, I have 1, right? Now, solve those two equations together, this one and this one, to get the values of c1 and c2. What's going to be the solution? So from the first equation, we can say that c1 equals minus c2. Plug that into the second equation. So 1 is equal to minus 3 times minus c2 minus 3 c2, right? Sorry, minus 2. Made a mistake here, minus. Yes, minus 2 c2, yes. Okay? So what's going to be the solution for c2? 1 minus 3 is plus, so that's plus 3 minus 2. Yes, exactly. So C2 is equal to 1. And then from that, then C1 is equal to minus 1. Okay? plug that into the equation, so you have yn equals minus e to the minus 3t, right, plus e to the minus 2t. Okay. Now, from this, we still need to take this and plug it into the expression here, right? So again, for this situation, before going to plug the yn, what's the value of b0? The order of pd is smaller than the order of qd, right? So this means that b0 is 0. So this term disappears, right? So we remain with h of t is equal to p of d, that's the derivative polynomial with respect to input for the input, right? Multiplied by yn. What's yn? Minus e minus 3t plus e minus 2t, right? And then the whole thing is multiplied by unit step of t. Now let's apply that polynomial, which is the first derivative plus 1, applied to minus e minus 3t plus e minus 2t, and the whole thing is multiplied by unit step of t. Now let's apply the derivative. So when you take the derivative, when you put the 1, you just get the same term. So that's minus e minus 3t plus e minus 2t, right? And then when you apply this to the whole expression, so you take the first derivative of this whole expression, you end up with 3 e to the minus 3t, right? And then minus 2 e to the minus 2t, correct? When you take the first derivative of this, you end up with this, right? Okay? And then just all of this multiplied by unit step of t, and just combine the terms together, so you end up e to the minus 3t to e to the minus 3t, and minus e to the minus 2t, and this whole thing is multiplied by unit step of t, and that's your impulse response. This is h of t for this system. Yes?
So it's d plus 1.
Yeah.
So derivative?
This means the same without any derivation, and then when it's multiplied by d, it means take the first derivative. If it's multiplied by d squared, take the second derivative, and so on. Okay? So this polynomial is an expression of the consecutive derivatives that you need to do. It's not like a polynomial of a variable, right? Yeah.
Where did we get the initial conditions from?
Because we are solving for zero initial conditions, right? And I said in the expression initially, right? Here, not here, but in the previous slide, we are solving for input given that the initial conditions are 0, right?
Oh.
So we say that.
It's just an assumption, yeah.
Yeah, you can call it an assumption, okay? But not all of them are equal to 0. There is one exception, which is the highest derivative one, right? I mentioned that in the previous slide. The reason of that is that your initial conditions are typically the values at time 0. But the problem is when you put a delta, the delta enforces some value at the time 0, right? So the initial conditions are, all of them are 0, even the highest order derivative, just before you reach 0. But once you reach time 0, there is a sudden change because of the impulse, okay? So that's why we get all the initial conditions 0, except the highest derivative. That one will have a value of 1. Where does it come from to be a value of 1? There is a mathematical derivation for that, but we didn't go through it, okay? Yes. So it's always, just before answering your question, so it's always going to be the y of 0 is equal to 0, the y dot of 0 is equal to 0, and so on, until the y n minus 1 derivative of 0, this one is equal. This is always your initial condition. For finding the impulse response, it's a 0 initial condition, which is always going to look like this. Okay? Yes?
So if we had d cubed, then we would have 3 equations in the exponential equation?
We are not addressing the case where the system is impractical, where we are not addressing the case where on the side, you are talking about the right side or the left side?
The left.
Ah, okay. If we have d cubed, what will happen?
3 yn equations and then 3 initial conditions.
Yes. Yeah. So we will have, yes, if we had D3, then we would have initial conditions up to the second derivative, okay? And those expressions are gonna be 3 exponentials, okay? Any other questions?
Can you just scroll down a little bit?
Okay. Any other questions? All looks good?
Can you just explain again why we did D+1 and why that is the derivative?
No, why we did D plus 1? D plus 1 is the expression itself says this is how H looks like. The expression says that H of T is equal to B naught delta, right? And then plus that term multiplied by unit step. And that term is the P of D applied to Yn. When we say polynomial of derivatives multiplied by something, it means actually derivation process or derivation procedure applied to that function, okay? So basically our starting point is this. And where did this come from? There is a mathematical derivation for it, but we don't need to do it in this course. I think the book has it in an appendix. If you want to look it up and follow the derivations, it's up to you. But I'm not asking you to do that. Just know that we can always use this expression to find the impulse response for any practical system where we know the input-output differential equation relation, okay?
What if it was D plus 2?
Sorry?
What if it was D plus 2?
If it was, where? Here?
Yeah.
This means 2 multiplied by, it's just simply,
Okay,
the number here is the function with whatever constant. If it was 2D, for example, this means derivative multiplied by 2, okay? Yes. You know, just before answering your question, you know, you studied, did you study maths for engineers?
No.
Ah, okay, so you didn't study the Laplace method for solving differential equations. Because this is exactly, if you remove this D and you think in the Laplace terms, this becomes an S expression, right? The exact same thing. But you didn't study it, so it doesn't mean much to you. Yes? What was your question?
I forgot.
You forgot your question, okay. When you remember it, I will be happy to answer, okay?
Yeah, I remember. But
Yeah.
B not,
I'm happy to answer.
B not, how do we find it if we have it?
It's gonna be okay. The example, for example, I actually gave some numbers in the previous slide, but I will imagine, for example, that originally, instead of this equation, the input-output relation was something like this: d squared, 2d squared plus dy of t is equal to d squared x of t, for example. Okay? In this case, the coefficient of this guy is gonna be your b naught. Okay? Yeah. So the highest derivative, which should be the same as the highest derivative on the other side in terms of the order, the coefficient of that highest derivative is your b naught. Okay.
And if we found the numbers to be complex, it's fine, or will we not do that?
Doesn't matter. No, you can encounter that. Okay, and also repeated. Sometimes you find instead of getting this nice thing, you get lambda plus 3 squared equals 0. So this means that the two values of lambda are the same. If you go back few slides, I addressed this case and the other case, the case of complex, right? In terms of how you can change the final expression. Again, you studied the details of that in your math for engineers or differential equation solutions, but here you just need to refer to those and plug the equations directly, okay? Any other questions? Okay, so